I'm going to leave this open and pull my calculator up because we'll be kind of going back and forth between them. So, okay, the last part here, the mysterious part that we haven't learned yet is T sub 4. And that's going to be something that's not using rectangles. It's another shape that is relatively easy to use. And anyone guess what shape? Yeah, trapezoid. Very good, trapezoid. So there's also a way to do a trapezoidal approximation. So let's go ahead and review a trapezoid. The trapezoid that we're going to use is not your typical trapezoid, but rather what we call a right trapezoid. And remember, a trapezoid has two bases, b sub 1, b sub 2, and it has a height, like that. So it looks kind of like a fallen over half of an Egyptian obelisk. If you stand it upright, it might look something like this. And you have b sub 1 and b sub 2, and your h is on the bottom. Well, this is what we're going to be drawing in our diagrams, and the bases end up not being bases at all. They end up being the function values heights at the left and right endpoints, and the h ends up being the width down at the bottom, which is delta x. Now, the area of a trapezoid is 1/2 b sub 1 plus b sub 2 times the height. So it's the average of the bases times the height. So what we're going to do now is go down to the bottom, draw our trapezoids in there, use the formula, and we're going to set them up for each of the 4 trapezoids. Then we're going to look for patterns, okay? So down here, if I do a trapezoidal, let's use something pretty prominent like beefy black. I would come here on this first interval and draw a line from one endpoint to the other. And if you notice that the first trapezoid actually looks like a triangle because one of the heights is 0, or one of the bases, I should say. Here's your next trapezoid down there. The next trapezoid, you connect these endpoints like that, and the next trapezoid, you connect the endpoints like that. All right, so when you see that, you can tell right away that it's going to be a pretty decent approximation, right? But it will be, bless you, too big or too small. You can tell definitively it's going to be too big here because the graph is increasing concave up. When you connect the dots, you just pick up these little extra slivers on each of these intervals. Okay, so here's what the area would be. The area, I should say the area approximation, here's what the trapezoidal approximation will be. All right, the first trapezoid is going to be a 1/2 times the sum of the bases. Well, the bases are really the heights, remember, at the endpoint. So it's going to be f of 0 plus f of 1/4. We're not using the 1/8, 3/8 anymore. Times the height, which is really now the base, delta x. I'm going to go ahead and keep it as delta x for now. Plus, that's the first one. The next trapezoid from 1/4 to 1/2 is 1/2 the sum of the function values at the two endpoints, f of 1/4 plus f of 1/2, times the base, which is delta x, plus the next trapezoid from 1/3 or 1/2 to 3/4 is 1/2 times f of 1/2 plus f of 3/4 times the width delta x. And then the last one, I'm kind of running out of room here. It'll be 1/2 times f of 3/4 plus f of 1, and then all times delta x. I got it. I got it in there. All right, so that's just 4 trapezoidal computations. Now I'm going to get that, cut it, and move it over here where we have some room. Where do we have room? Oh, I don't have room. Let me add a page below. All right, so here I have room. You don't want to run out of room. Get more paper or whatever. Okay, so did I grab the whole? I didn't even grab the whole thing. Oh, okay, thank you. So I just need to, yeah, there we go. Okay, there we go. Crisis averted. All right, so there it is. Now, what do you notice about all the terms? It is long, as Rap anticipated, but each term has a 1/2 in it, right? And because it's common in each term, we can factor it out. And the delta x, very good, which I'm going to leave as delta x for now. Now, notice when you factor those two things out, you're going to have just f of 0 plus f of a fourth plus f of a fourth plus f of a half plus f of a half plus f of 3/4 plus f of 3/4 plus f of 1. Eh? Thank you. And notice that you're going to be able to combine like terms. So it's going to be f of 0 plus f of 1/4 plus f of 1/4, which is 2f of 1/4 plus reverse poetic plus 2 times f of 1/2 plus 2 times f of 3/4 plus, it looks like we just have plus f of 1. And this right here is your trapezoidal pattern that you want to memorize. If you notice, 1/2 delta x, if delta x is uniform, and in this case it is, we found it, it's always going to be able to be factored up front, 1/2 delta x. You're using all the y values now. Whenever we did the rectangular method, 4 rectangles had 4 terms. We now have 1, 2, 3, 4, 5 terms. So we're using all the y values, but notice the ones on the end are only used once, and all the y values on the interior are doubled. So it would appear that the sum then will be twice as large as the one for the rectangular approximations. And it will be approximately. But that's why that 1/2 is out front, to cut it back down to size. Now, of course, I think you can see why we have double on the interior. You can think of this as like some kind of multifamily living complex where you have these interior walls that are a wall for both sides. Okay, it's a right wall for the left side and it's a left wall for the right side. So they're used twice, but the y values on the endpoints are only used once. They're exterior walls. All right, so memorize this pattern. 1/2 delta x times the sum of all the y values, but you double the ones on the interior. That's trapezoidal, when delta x is uniform. All right, let's go ahead and compute it now for our function. What is r delta x? Got to think back. It was a fourth, wasn't it? And our function is x squared, so we're squaring our input. So here we go. 0 squared plus 2 times 1/4 squared is 1/16, plus 2 times a half squared is a fourth, plus 2 times 3/4 squared is 9/16, plus 1 squared is 1. So that ends up being an eighth times, let's see, we get 1/8 plus 1/2 plus 9/8 plus 1. I'm going to call 1 8/8 if you're okay with that. So let's see, if I add that up, I get 18/8 plus 4/8, that's 22/8. 22/8. And that simplifies to 11. Is that right? 1/4. Did I square it right? 9/16 to 0 1/8 1/2. Maybe I'll check in my work. 9/8 8/8. Yeah, okay. 11/16. 30 seconds. Thank you. Yeah, thank you. 11 30 seconds. Wow. Okay, wow. A little after lunch blip there. 11 30 seconds. 11 30 seconds. How many 30 seconds? 11 30 seconds. 11 30 seconds. 11 30 seconds. 11 30 seconds. There's 11 30 seconds. We did that before lunch. So it turned out that the trapezoidal approximation ended up being the same as the average of the left endpoint and right endpoint. You think that's coincidence? Or will that always be? Yeah, that will always be. That will always be. Because if you think about it, we're just drawing a straight line from one endpoint to another. And so it's assuming a constant rate of change in between the endpoints, which should be the average of the two endpoints. And you can actually prove that mathematically. So it turns out that there are now two ways to find the trapezoidal approximation. You can either A, use this pattern, which I would recommend if you just were asked to find it trapezoidally, right? 1/2 delta x, add up all the y values, double the ones in the interior, or find the left endpoint, find the right endpoint, and using correct notation show that you're finding the average of the two. You can do left endpoint, then right endpoint, and then average them. Yeah. Yeah, but it's a little bit more work, actually. Now, if you're asked to, like, do the left endpoint and then the right endpoint and then the trapezoidal, since you already have the left and right, that makes more sense to just do the trapezoidal. But the trapezoidal pattern is something that I do want you to memorize. It will be useful in its own merit, okay? And there's another method for approximating called Simpsons Rule that actually uses not straight lines between the dots, but curves between the dots. And it actually gets a little bit more accurate than these. But all methods, as you choose more and more rectangles, converge upon the actual. All right, now let's go to the calculator and see what the actual area is. What I'm going to do is graph the in the calculator y equals x squared. I'm going to graph it in the window that we had from 0 to 1 on the x-axis and 0 to 1 on the y-axis. And I'll show you what it looks like. Let's see. If I graph x squared, it's not showing up because I turned it off for a good reason. Here we go. You ready? It's going to be pretty. It's going to be blue. Unicorn blue. There it is. Ooh, nice. There it is. Now, from the graphing screen, we've done this before. Second trace is your menu. We've done 6, right? dy dx, we've done that before. If you want to know what the slope is at 0.5, at 1/2, you can plug it in, and it gives you dy dx equals 1. We've done that, numeric derivatives. But look what happens if you go second trace and look below number 6. There's, looks like SFF of x dx. Well, we know that now to be the integral special effects of dx. So if you choose 7, the lower limit is your lower bound. We're starting at 0. Hit enter. The upper limit, we went all the way to 1. Hit enter. Prepare to be oohed and awed and oohed. Ready? Ooh, ah, ooh. Purdy, purdy. And now look what it says. It says the special effects dx is 0.33333333333, which we know to be 1/3. Guess what the actual area is of this? 2/6. Very good. 1/3. It's actually 1/3. It's actually 1/3. The actual area is 1/3. So we could actually figure out, let's see how close some of these approximations were. The left end point was 7/32, which we said was going to be too small. 0.218. Yeah, that's pretty close to 0.3. Not really. The upper bound that was too big was 15/32. And 0.468. Yeah. It's close-ish, right? Now the midpoint was 21/64. Let's see how close that one was. Remember, for all things being equal, the same number of subintervals, this one should be more accurate than the left and right in general. 0.328. Nicht so schlecht, right? Not so bad. Now the trapezoidal, which was also the average of the two, we knew it was going to be what? A little too big or a little too small? A little too big because it was concave up and increasing. So 0.343 it was. So it turns out that the midpoint was a little too small. That's not really easy to tell from the curve, but the other three were. Yeah, so there you go. They're all pretty good, but the trapezoidal and the midpoint, all things being equal, they're a little bit more accurate. Now let's look at this right here. If we wanted to be more accurate than that, we could certainly just choose more rectangles, right? But for us, it's going to be more tedious to compute. So here's a diagram of using a right endpoint with 10 rectangles. You get 0.385. 30 rectangles, you get 0.3502. 50 rectangles, which you could barely see now, you get 0.343. Now, after 50, it gets hard to draw them. So if you go to the chart, notice if you use 100 rectangles for the right endpoint, you get 0.338. 1,000 gives you 0.3338. So watch this. You see a limiting process here. As n increases on the right endpoint, 0.385, 0.358, 0.350, blah, 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 0.333, you can see that the areas are decreasing, but there is a apparent limit to what they're approaching, right? And that value is 0.333. So they're approaching the actual area from above. Look at the left endpoint column here, 0.285, 0.308, 0.316. These numbers are increasing as n goes to infinity, but they also appear to be approaching 0.33333. And that's true for the midpoint method. It's true for the trapezoidal method. The more shapes you use, the more partitions, the more tedious the calculations for us, but the more accurate the calculation. Okay, so there you go. That's pretty interesting. Now I'm going to show you what we just discovered, okay, and kind of give you a preview of coming attractions. What we just found was the actual area to be 1/3. The calculator helped us. We're going to go ahead and write that like this. The area is going to be the integral, we say, from 0 to 1 of x squared with respect to x. And we know it's going to be 1/3. Okay? We call that the definite integral. And the definite integral gives you a definite answer. And in this case, the definite answer is definitely 1/3. And it represents the area of the positive region above the x-axis but below the curve. Okay? Now, there is a way to compute it by hand. Okay? And I am going to show you how to do that right now. This will be a preview of coming attractions. I'll squeeze it in right here. If I wanted to evaluate the integral from 0 to 1 of x squared dx, that's a definite integral because you can see the 0 and 1. Let's take away the intervals of integration, as we call them, for a second. If I asked you to evaluate that, what would you do? That'd be an indefinite integral. You'd find the antiderivative, right, which is 1/3 x cubed plus c, right? The only difference when you have values there, you put the when bar at the back, and you evaluate it, we say, from 0 to 1. Now, what I'm about to show you is called the fundamental theorem of calculus. And this is how you can evaluate it. All you have to do is substitute in the right endpoint, plug it in for x, and you get 1/3 plus c, minus, always minus, then you plug in the lower bound, the bottom number, and you get 0 plus c. Now, what happens with your c's? They cancel, and you're left with 1/3. And that's the answer. Yeah, nifty. To say it succinctly, it's nifty. All those methods we just did, all those arduous methods, the painstaking methods that took a long time, they were very detail-oriented, just to get approximations that weren't really necessarily very good. It's unnecessary in this case because we have a shortcut method, essentially, that's pretty nifty, that allows us in much less time to get a much better answer, the exact answer. Very good question. How did that come into being where we could just go from here to here? That's a very good question. This method is very heavily dependent on you being able to find an antiderivative. Not all functions have an antiderivative or a known antiderivative, and so the only way to do it is numerically. So those numeric methods that we just did, that was the precursor to this, but today they still have relevance, right? Computers can do that. In fact, I think your calculators use some type of Riemann sums in their program to compute areas. They don't. The 84s are not computer algebra system machines. They're number crunchers. So for programming purposes and for functions that don't have known antiderivatives, you can't do this. The numeric methods are viable. But it was the work of a student of Gauss who kind of came up with the nifty shortcut, if you want to think about it. Gauss is up here. Oh, that's Descartes. This is Gauss. Oh, that's a different dude. Yeah, this was George Bernard Riemann. He was also German, and he's a very pleasant man, as you can see. He's telling you hi right now. You don't even know that. Relatively recent. Yeah, relatively recent. And I kind of showed you this idea yesterday. Without getting into the specifics, like we did with the limit definition of the derivative, this is kind of the limit definition of the definite integral. The area of a positive region is the limit as n goes to infinity. You let the number of rectangles go to infinity of the sum from left to right, from A to B, of all your heights, which are your f of x sub i's, all your heights, times your widths, which are your delta x. And without getting into the magical step, just know that that became equals to, the sum became the integral symbol, okay, which is still an s, from A to B, of your integrand, which was your height, f of x, and the infinitely small dx replaced the measurably small delta x, okay? And it's the fundamental theorem of calculus that we'll learn in the next section that essentially allows us to evaluate that. But it is dependent upon knowing the antiderivative, okay? Pretty cool. Now, because he was a pioneer in making that leap, Riemann, we kind of named some of the methods after him. So if you come back up here, anytime you're using a rectangle, whether it's a left, right, or midpoint, we call the rectangular methods the rectangular approximation methods, we call the method of Riemann sums. So if you ever heard the word Riemann sums, that just means use rectangles. And it's very easy to remember Riemann and rectangles because neither one have a Q in the name, right? That's how you remember. Riemann, rectangles. Rectangles, Riemann. No Q sound. Okay? The trapezoidal approximation is not Riemann sums. Riemann sums are what shape? Rectangles. Now, it's kind of funny because for the most part, if we can find the antiderivative, we don't need to use Riemann sums. So the very method that Riemann helped pioneer and give to us is something that we use instead of the process that was named after him to honor that method, and so he's forgotten by his own method. Yeah, no, there's no bad feelings. It's an honor. Riemann sums, the method of Riemann sums. Okay, let's look at example 3. Geometrically. Let me show you one last thing before we move on. Sorry, going back to the previous one. I get excited sometimes to move too fast. Remember? We even saw it live. It took a while, right? Well, that thing is shading and graphing. The clock is ticking. Time is money, money is time, right? We're not going to do it like that moving forward. It's pretty, but here's how we're going to evaluate. We're going to go do it from the home screen. So from the home screen, we're going to hit math, and not 8. We've done that enough. Math 8. We're going to go to math 9. F-N-I-N-T. Yeah. F-N-I-N-T. 9. If you do that and you have math print, it shows up like this. It's a template for the definite integral, which you can also, I think, get from an alpha shortcut. But if you just type it in, 0, click up to 1, come down here, type in x squared, go to dx, type it in just like it would be on the definite integral, you get 1/3. You can even hit math enter, and it'll tell you it's a third if you're not sure. That's pretty cool. Come on. Well, normally, it's frozen. It's frozen. Okay, anyway, it worked for a while. So that's how we're going to be doing moving forward. We're not going to go to the graph necessarily. It's quicker. You don't have to wait for the graph. And you also have values on the home screen that you can quickly store and reuse for other calculations. So anyway, if you have the classic print, when you do that, it shows up as F-N-I-N-T, and it's a slightly different argument, which if you have one of those classic print, come see me. I'll walk you through it. Okay, so what we're going to do now is look at this example. We're going to evaluate the integral from 0 to 4 of 2x geometrically. Okay, so step 1, we know that kind of now means to find the area of the region bounded by that graph in the x-axis from x equals 0 to 4. So you might want to identify the region. 2x is your line that looks like this. It passes through the origin, has a slope of 2. That's the graph of y equals 2x. And we're looking from x equals 0 to x equals 4, and then dx means bounded by the x-axis. So we're looking for this. Now, it doesn't say to approximate the integral. It says to actually find the integral. We don't need to use any approximation methods, Riemann sums or trapezoidal, because we recognize that shape as a triangular, triangle. Very good. And we have the formula for the area of a triangle. So the integral from 0 to 4 of 2x dx is going to equal 1/2 the base times the height, yeah? It's a right triangle. So what's the base from 0 to 4? 4. The height should just be the function value at 4, which is 4 times 2 is 8. And, of course, half of 4 is 2 times 8 is 16. So there's the definite integral. And it represents the area of the region. How about that? If the calculator wasn't frozen, we could do it on the calculator, and guess what? It would know that it's 16. Okay? Now let's do it the other way. This is kind of officially doing it a way that we don't officially know how to do yet. It's in the next section. If I wanted to do it using what's going to be known as the fundamental theory of calculus, that is the nifty shortcut rule, I need to be able to find the antiderivative of 2x. Do I? Is that a tough one? No, it's pretty tough, right? Sarcastically. It's x squared. Now, if you notice the plus c's canceled out, right? Because it's a definite integral, your plus c's will always cancel. You do not have to show the plus c on a definite integral. If you have the numbers on the upper and lower bound, and you're not going to lose points for not showing them, because everyone knows you're just going to cancel. All right, so here we go. We got x squared from 0 to 4. We plug in the top, and we get 4 squared. Minus plug in the bottom, we get 0 squared. And, of course, that gives us 16. So all methods give us the same result, which is nice. Nice. Thank you, Riemann. Thank you, Riemann. Thank you, Riemann. You're welcome. All right. Let's talk about area under the curve very quickly here before we get out of here. We have just looked at two integrals of two regions that were positive. They were the graphs of the y values were all above the x-axis, namely non-negative. Okay, non-negative means it can't be what? Negative. It could be positive, like the y values like we saw, or it could be 0 at the very least. If you have a function that is non-negative on a closed interval from a to b, then we say that the area under that curve, or the graph, if it's not a curve, from a to b is defined to be the definite integral from a to b. Okay, so remember that a is the lower bound, b is the upper bound, and a is less than b because we're on the interval from left to right. So we read this as the integral from a to b of f of x with respect to x, or dx. And that's only if f of x is greater than or equal to 0 on the interval. Okay? Now notice if it says you have a non-positive region or a negative region. If you have a function that's entirely negative on the region, is it possible then that the integral could represent the area? Well, very quickly, let's see here. If I had the graph of y equals negative 2x instead of y equals positive 2x, and I look from 0 to 4, I could find the area of that shaded region, right? The area of that shaded region is still 1/2 the base, which is 4, times the height. The y value there is negative 8, but I know heights can be negative, so I know the height is still 8, and I still get 16. So I know the area of that region is 16. Well, look, if I try to evaluate it from 0 to 4 using my shortcut, nifty fundamental theorem rule that I don't really know yet, what would be the antiderivative of negative 2x? Negative x squared, right? Add 1 divided by 2. No plus c needed. Evaluate that from 0 to 4. Now that's negative 1 times x squared. So that would be a negative factored out. Plug in a 4 minus plug in a 0. You end up with negative 16. Is it possible to have an area of negative 16? There's no way to have a negative area, right? You go to the paint store and tell them you have a room that's negative 16 square feet and you need enough paint to cover it. I don't know what they do. In the empty can. They give you money. Say, get out of the store. Leave us alone. Okay? Now, we can use this number, right, to determine the area, can't we? What'd you say, Rap? All we have to do to get the area of the region is do what with the negative? Take the absolute value of it, or take the opposite of it. And that's how we'll finish today. If you have a region that's entirely negative, the area is the opposite of the definite integral from left to right. Because you're going to get a negative number because your y values are. Yeah, that's right. Negatory. All right. Have a great rest of the day. We'll see you mañana.